Okay, having talked about deep learning, let's now talk a little bit about the second aspect of my talk, namely natural language processing. So the first thing to keep in mind is that natural language processing is, even though it has like natural language inside the acronym or inside the phrase, it is neither linguistics nor digital humanities. So linguistics and maybe also like digital humanities, at least the part of digital humanities that deals with language, is focusing on language and um, on linguistics in a more general and like more abstract sense, whereas natural language processing is usually very applied, and it's oftentimes until today it's solving tasks. So there are some problems such as determining the part of speech labels for all the words in a sentence, or classifying a sentence, or classifying a document, which even linguists don't even bother to deal with because they think that these tasks are quite simple tasks. So they would typically not take such problems into account at all. But that does not mean that there are not other problems that lie in the intersection of those different disciplines. But usually, as I said, NLP is an applied field that is trying to solve some oftentimes low-level problems in natural language using the computer. But nowadays, it also goes up to like higher and more difficult tasks such as argumentation mining or like emotion and metaphor detection. So these are also difficult problems from the point of view of linguistics. So this is also in the intersection of those fields. A key difference here would probably be that linguists deal with such problems in a more abstract and high level way, and in a more methodological way also. So they want to really develop theories about this, whereas we just aim to like solve the problem. So we usually have annotated data, and we try to develop computer models that can solve the problem with maximum accuracy, for example. So when we look into natural language processing, so there is a distinction that I typically make. So we have like three classical or like three prototypical tasks in natural language processing. The first task is we label a sequence of words. So this could be a sentence or a document, and we want to attach one label to it, or in some cases it could also be a few labels, like 2 or 3 labels, right? As we've already, yeah. So this could be like when a sentence or a document falls in several classes. For example, a document could be both about sports and politics, right? So, but anyway, so this first class is we have a longer text document, and we want to attach either one or a few labels to it. The second class is what I call sequence tagging. In this class, we want to label each element in our sequence. So the sequence could be a sentence. This is the most classical situation, but it could also be a whole document. And in this longer sequence, we want to label each individual token, each individual element. So for part of speech tagging, that would be we have 1, 2, 3, 4 input words. So we also have 4 labels. So and the final problem class is even more difficult than the previous two. In this case, we don't want to label the whole text, and we also don't want to attach a label to each element in the text, but we want to rewrite the input text. So this is also called sequence-to-sequence modeling. And a classical use case is machine translation, where, for example, you have the English sentence and you want to translate it into German. And this is more difficult than the previous two, because in this case, Um, One thing that can happen is that you have no order help. So with order help, I mean, so the input ordering doesn't indicate to you which kind of output you should have. Whereas this is true in sequence tagging, where you know that the first word has the first label, the second word has the second label, the third word has the third label. And in classification, we don't have such a relationship in the first place. But in machine translation and sequence-to-sequence modeling in general, the order of the input does not need to relate to the order of the output. So the order in the elements of the input does not need to correlate to the order of the elements in the output. And this makes this problem the most difficult one and the most challenging one. Good. Now let's ask, if we want to do deep learning for natural language processing, which two ingredients do we need? And I would say that we need two ingredients which help us to set up the problem. And the first one is, we know that deep neural networks or neural networks, they have an input, right? So there's some input coming in, as we've previously discussed. And this input comes in numerical form. So we need to somehow put a vector into our neural network. So that's not a discrete input like a word or a text as a symbolic representation, but numbers are coming in. Now the question is, how do we get those numbers? And the second one is, which neural network architecture should we choose? So as we will see in the following, the deep learning community has come up with different architectures. So we have already seen two architectures. The first one was this perceptron, and the second one was the multi-layer perceptron, which also had hidden layers. So these are just two architectures. We're gonna see different ones. And now the question when we apply deep learning to one NLP problem is, which architecture are we gonna shoot at our specific NLP problem? So when we talk about the representation, we're gonna be talking about what has become very popular under the name of embeddings, and I will introduce those embeddings in just a few slides. When we talk about the architectures, here's a couple of architectures that I will introduce in the following. This is perceptron, multi-layer perceptron, recurrent neural network, which has like LSTM as its most famous instantiation, convolutional neural network, also abbreviated as CNN, and the encoder-decoder neural network architecture, which can either be based on RNNs or like transformer-based models, which I will also briefly introduce. And then I have said in the slide before that there is this classical categorization of NLP problems into classification, sequence tagging. So here's classification, sequence tagging, and sequence-to-sequence models. And now, so there's a natural relationships between these NLP, these high-level NLP problems, and the neural network architectures proposed. And this is the one that I've shown here. So if we want to do classification, would usually use a perceptron or a multi-layer perceptron or a convolutional neural networks, because all these architectures are able to like take an input representation which represents, let's say, a word or a sentence, and attach a label to it. If we're gonna be dealing with sequence tagging, then what we would use is an RNN, and this is because sequence tagging involves like labeling each element in a sentence or in a document, and for this it would be good to have like a like a recurrent relation. So once we label the 10th element, we would have a look at the 10th element itself, but we would also take context into account. So we would have to be somehow referring this label for the 10th element to the input at time step 9, or also maybe the label for the 9th element. So we would kind of have to relate to the previous input and maybe also to the future input. And in this case, these recurrent neural networks, as you can see even just from their name, they have such recurrence relationships that allows to take the past and the future recurrently into account. And once we're going to be dealing with sequence-to-sequence models such as machine translation, we would use encoder-decoder models, as I will introduce below. Basically, encoder-decoder models consist of two models. One is the encoder and the other one is the decoder. So the encoder could be any of those model classes up here. Typically, that could be an RNN or a transformer model. And what the encoder is doing, well, it encodes, it gives a numerical representation for our input. So like we first numerically represent the input using the encoder, and then we decode this numerical representation using a decoder, and this decoder then generates the output string. Okay, let's talk about the first thing, which is input representations. So, as I've said, a neural network takes a vector as an input, so it takes numbers, like a sequence of numbers, if you want, as an input. And in NLP problems, the inputs that we have are like characters, words, sentences, or whole text. So, also our vectors could represent each of those linguistic units. And what do we demand about our vector representations? They should somehow encode the semantics, which is the meaning of the unit. So what does it mean? What does the word cat actually mean? What does this sentence, I like cats, actually mean? What does the character C actually mean? But on the other hand, we would maybe, for some task, also want that our representation somehow takes the grammar into account and the syntax, right? So it also would be beneficial if we have somehow encoded grammatical relationships. Let's say you have a language which has a lot of inflection, such as German. So we would somehow also want to know that the word Katzen is the plural of the base form Katze, right? If our model would somehow, or if our representation would encode this, maybe this would have beneficial properties. And also, if we talk about encoding a whole sentence, it could help us not only to understand the meaning, but also like know something about the grammar. So Pete likes Jane is different from Jane likes Pete, and this is a difference in order, and order could also be seen as a property of syntax. So here you also see it would be good to know something about this syntactical arrangement of the units in a text. And this, of course, where here you also see that syntax and semantics go together. So these phenomena are interrelated anyway. So we'd hope that our representations would capture both of them, at least to some degree. And the property that we want, of course, is that similar objects have similar representations. So if two sentences mean the same things or have the same grammar, we would want that our numerical representations are very similar, and the same goes for characters, words, and whole text. And this is because if those things are similar, they often have the same label that's coming out, right? If two sentences are very similar, and probably our natural language processing task in the end requires the same label for those two objects. Therefore, we naturally want that we have a similarity in the numeric representations once the underlying objects are similar. Good. So these are the use cases. A classical scenario involves just looking at words and looking at their semantics. So now, how do we infer the meaning? Semantics is the field of studying the meaning, and this meaning, let's now say we are talking about words. So there's a definition that you could use for what it means that two words have have the same meaning. And this definition could be if they are interchangeable in all possible contexts. So if you can replace one word with the other in all possible contexts, then most likely, or even we could take this as a definition, then those two words have the same meaning. And this means that the context really informs us about the meaning of words, as we can also illustrate using those two example sentences. The first one being, he filled the wampumuk, passed it around, and we all drank some. So let's say you enter a new language community. You've never heard this word wampumuk before, but from the meaning you could infer now what it would probably denote, and you would guess that it denotes something like wine, or like some bottle, also, right? Something where you put liquid inside, because they're gonna pass it around and they're gonna drink from it. So that's most likely gonna be some bottle to with liquid. Good, so the context gives us a clue about the meaning of the word. And in this other context here, we found a little hairy wampumuk sleeping behind a tree. So you have all this context here. It's hairy, it's small, it's sleeping, so it's probably an animate thing. So it's probably gonna be an animal. It's also behind the tree, right? So it's in the nature. So animals occur in the nature. They have hairs, and typically most animals are smaller than humans, so they are small also. So that's probably gonna be an animal if we change the context, right? So, and all of this is summarized in this distributional hypothesis. You shall know a word by the company it keeps. Now, how do we implement this hypothesis in with the computer? And there's one famous model that implements this hypothesis, and this model goes by the word2vec, by the name word2vec. So, and there are two instantiations of this, which I just want to briefly touch upon. So, in the first model, what we want to do is we have the context and we want to predict the center word. So from the context we predict the center word, or we do it vice versa. From the center word we predict the context, right? So this one seems a little harder than this one, but computationally they are very, very similar. And why does this make sense? It makes sense because we say that if we know the context of a word, we know also its meaning to a high degree, right? And that's why it makes sense to use such a model to capture semantics. Now, how is that implemented in practice? You see here the two different realizations. Let me talk about the skip-gram model. So what's coming in here is a word index. So we say that what's coming in is the 10th word in the vocabulary. Let's say you have, in English, you have a vocabulary of 100,000 words, and you say now the 10th word, and you sort this in any manner that you want to sort. So this index really doesn't play a big role, right? It's just like the 10th word in any ordering of the words that you have. Maybe it's alphabetical ordering, right? And what you then have here, so this is a neural network. So we feed our input representation through a neural network, and you see here are multiple outputs. So we feed it in the first layer and then to the output layer. And in the output layer, we again have the we again want to predict, what we want to predict is the context word. So the word that appears two words before this word, the words that appears one word before this word, the word that appears one word after this word, and the word that appears two time steps after this word. Okay, so that's what we're going to predict, and it's very similar for the SIBO model. And what we say again, these indices, they can be represented by one-hot vectors. So the one-hot vector would be, let's say the cat is the second word in our vocabulary, so it would have a 1 at the second position, and if love is the fourth word, it would have a 1 at the fourth position, right? So this is our representation, And for the output, actually the same, but the output is a little bit misleading because the desired output is a one-hot vector, but what our neural network is typically putting out is not a one-hot vector, but in practice gonna put out something which has like real numbers in there, but those real numbers, they should like approximate a one-hot vector. And the cool thing is, so you know that the layers in a neural network are connected by a matrix, and we call this matrix here E. This is our embedding matrix that connects the inputs with the first hidden layer. And why do we call so we call it E? And after so now the whole thing about this model is after we have trained our neural network, so we're gonna train this to solve this task, and once we've trained it, we forget about this task. We don't actually want to predict the output, we only want to have this embedding matrix. Because this embedding matrix actually stores the vector representation of this word, of this input word, right? Because actually what we want, I said the motivation is to get an input representation. So we have this embedding matrix here, and it stores the input representation for the word with index I. And why is it doing this? Let's look at the illustration. So as I've said, after training is finished, we only care about the matrix E. And what we do is we multiply. So what E is doing, it like the operation that is being conducted here is a multiplication of the input vector, which was a one-hot vector, with this matrix E. And when we do a row, a multiplication of a row vector with a matrix, we get exactly the row vector that is at position I in the matrix. So we have here, this is position 1, 2, 3, 4. We get the fourth row of this matrix here. And now this fourth row is the vector representation of the fourth word in the vocabulary. If the fourth word is love here, then it would be the vector representation of the word love. And intuitively, and that's what we would gonna be using now. And then we can store this, so we can store our English vocabulary of, let's say, 100,000 words, and associate with each of those words a vector. And this is the vector that we're gonna associate for the word love, let's say. And now we can check whether similar words have similar representations. Well, they should have. If the words are similar, they have similar context. So the representation that we get when multiplying the input word, let's say love and like, they have the same context. So when we apply the index with the matrix E, it should actually give a similar representation here, because from this representation we're going to infer the context, and if we have similar representations we can infer similar context. So we would actually hope that our network learns to give similar vectors to love and like. And now this is what we check empirically. We're going to check whether semantically similar words are near in our vector space, right? So now we have for each word a vector, so this induces a vector space which we can somehow visualize. And observation number 2, which I will not go much into because that was not our focus, is like grammar is somehow also encoded in this vector space. And the first property, semantics, is what we're going to do is we're going to take all our English words, we get their vector representations, and then like this is like usually a 300-dimensional vector representation. We cannot visualize a 300-dimensional vector representation, but we can. There are techniques in mathematics like that project those 300-dimensional vector representation down to a 2-dimensional representation, and in 2 dimensions we can actually visualize the objects. And what we do from a typical run of this word-to-vec model on data, so we train this model on a big corpus for many epochs, and then we're gonna plot the vector representations in a vector space. Now what you can see here is that similar words actually appear close to each other. So you have like, here you have refrigerator, oven, microwave, they are all close together. And here on the right you have like charger, battery, Bosch. So these are like So these are like tools, and these are like um, well, these are things that you use for cooking. So those things have similar meaning and they are close to each other in vector space. This is now an empirical observation, and this is an empirical confirmation of our underlying theoretical construction, namely that this model is suited for representing semantics. And when we talk about syntax or morphology, so these are more grammatical properties of words, what we find here, for example, is we find some things such as, let's look at this example here, that walking and walk, so these are different grammatical properties of a word. So this is the gerund and this is the past. And what we find is they are close to, they have the same relationship to each other than the words swimming and swam. So swimming is also, this is again the gerund and the past. For two different verbs, they stand in a similar relationship, and this relationship is given here by this offset vector. So basically what it means is, if you want to go from gerund to past, you go a little bit to the right and then you go up. So, and then you could do this for other verb forms also, and you would find this relationship holds in the vector space. This again is an empirical observation, that once you do this this operation, you can get the different grammatical forms of a verb. So, like magically, our model also encodes syntax and grammar and morphology. So embeddings were very popular. So like in natural science, if something is successful, it reproduces and it generates a whole species of generations, and those generations are interlinked with each other. So we have a mother and a father, and they're gonna produce a new child. So we have like two models. Let's say a model inspires two other models, and these new models again inspire other models. And the same has happened with those embeddings. They were extremely successful. So people derive different embedding models. For example, embeddings that capture better grammar have been proposed, like more syntactically oriented embeddings. Embeddings that work on the level of characters have been proposed. This is relevant for languages that have a high degree of inflection, such as Turkish, German, or Czech, where you have a lot of intra-word variation. So in German you have lieben, liebte, geliebt. So these are different variants, and it would be good to model such phenomena on the character level. We also have multilingual embeddings. So these model words in different languages in the same vector space. So that's also something very cool. So we have like German and English in the same vector space, so that words that are translations of each other are also close to each other in the vector space. And finally, the coolest thing that nowadays we have are those contextualized embeddings that I will talk about in just a short while. So as I've already indicated, one of the most interesting use cases is to induce embeddings across multiple languages in a shared space. And this is illustrated here for English and German. What you see here is that the vector representation, so this is again a two-dimensional space. Each point is a vector corresponding to the word that is attached to the point in the space. And what you see here, like in blue is German, in red is English, and you see that this is indeed a shared feature space, a shared embedding space for English and German. And you see that you can see this from the fact that not only are similar words within each of those two languages, such as child and man, bike and car, eat and drink, close to each other, but also across different languages. So you have like man and Vater is close, even though they are from different languages. Trinken and drink are also close in the vector space. And such a shared representation space is really cool because now if you train a model, let's say in English, with features, with the representations or features in this space. So I use the term representation and feature here synonymously. So if you train such a model in a shared vector space using only English data, for example, so English data is labeled data is very plentiful. So you have, let's say, a training data set where you have an English document or an English sentence associated with part of speech labels. Then once you've trained this, you can apply this not only to English but also to German data, because your features are in a shared space, so that if it sees the word trinken, it would know that this is very similar to the English word drink, which it has seen in the training set, right, or in the training data. So by having a very similar feature representation, we would also have a very similar classification or decision of the machine learning model. Good. The other very important extension of those embeddings are contextualized embeddings. So, and these are very plausible. So once those contextualized embeddings are there, you would actually wonder how people ever came up with those initial embeddings, which we nowadays would call static embeddings. So those static embeddings assigned each word a vector, but you know that the meaning of words can vary depending on their context. So in different contexts, words may have different semantics, as you see by illustration of the word can here. If you see it in the context I can see you versus the context please give me that can, so you'll easily identify that in one case it's a verb, it's a modal verb, and in the other one it's a noun, and the meanings are totally unrelated and totally different. So you would better give a word a representation that varies with its context. And those contextualized embeddings have become extremely popular after 2018, and they have almost completely replaced the previous static embeddings. And the most popular model initially was Elmo, but that didn't last very long. Nowadays, everyone's using a variant of the BERT model, which I will then outline here. So again, to have the idea of the contextualized embeddings, check it here. We have the word mouse, which again has different meanings, like intuitively in English. So on the one hand, it could denote an animal. On the other hand, it could be associated to a computer. And if we assign this word mouse contextualized representations and then check those representations, you will see that the computer mouse really gets different representations. Or you see here in each sentence, in each context, even the computer mouse gets a different representation, and the same holds for the animal mouse. But still, they lie like in orthogonal dimensions of the space, indicating that these Elmo embeddings in this case give really a plausible vector representation to each instance. Now with BERT, the cool thing is BERT is not only embedding representation, it's a whole architecture, as I will just outline in the following. And this BERT architecture has been pre-trained in English on huge amounts of data. And by combining these two aspects, on the one hand, contextualization of the representations, and on the other hand, pre-training on huge amounts of data, it has really seen a lot of English text. So this BERT model is really a very powerful model, as I will, and therefore it has really pushed the state of the art in natural language processing quite a bit. So the idea is you pre-train BERT on this huge corpus, and you pre-train the contextualized embeddings, and then you take the same architecture and use the same architecture for your labeled data. So let's say you have a small labeled data set where you do document classification. So you use your pre-trained BERT model that knows a lot about the English language already, and you apply it to document classification. So basically transfer its general language understanding abilities of English to a small amount of label data set, and therefore like it has really like immensely pushed the state of the art, and nowadays almost everyone is using this architecture or a variant of the BERT architecture. Let's quickly look how BERT is actually working. So it has this pre-training step, and then the other step when you apply it to your own data, it's called the fine-tuning step. So it has those two steps. And in the pre-training step, it takes English sentences and it solves some unlabeled tasks, self-supervised tasks. So self-supervision means actually no human is involved in the labeling. So instead, what it's doing is it's making its classification task itself, so to speak, by just taking English data and masking out words in the input text. And then BERT is trying, the BERT architecture, so that's the BERT architecture, is trying to predict the missing words, right? So you just like in each sentence, randomly some words are hidden, and BERT is trying to guess what the missing words should actually be like. And it's optimized on this self-supervised task. And solving such a task is actually intuitively plausible, because if you know the missing words, you really acquire language understanding, right? So in this way, it's hoped that BERT is acquiring general language understanding, and then you can apply this by doing some fine-tuning on your specific task. And your specific task could be anything. It could be named entity recognition, question answering, whatever you have, right? So you could apply it to multiple tasks. And in this way, really, BERT transfers its general its general knowledge of the English language when it to the specific downstream task, and it can leverage this specific knowledge when dealing with each individual downstream task. Okay, so this is BERT. The final thing that I will very briefly talk about is sentence embeddings. So we've seen up to now embeddings for words, but I've already indicated that you can also get embeddings, that is vector representations for other linguistic objects such as characters, syllables, morphemes, and whole sentences, and even whole texts, right? So in here I want to briefly outline two ideas for inducing representations for sentences. So there I want to differentiate those approaches into simple methods and complex methods, where the simple methods would, for example, take the average embeddings of all the words in a sentence. Assume you have a sentence with 20 words. We already get our word embeddings, let's say from word to vec, and then we just average those word embeddings. So this is a simple and cheap method, which has many deficits. For example, even if the order of the words in the sentence changes, the representation will be the same. But on the other hand, it has been shown that in many tasks, such a simple representation is actually sufficient, for example, when you do document classification, because there it really matters oftentimes it suffices to know which words appear in the sentence without knowing their exact order. And then there are more complex methods that overcome those limitations of the simple methods, where, for example, you have a recurrent neural network, which is a more complex architecture, trained on top of word embeddings in a supervised manner. For example, you want to solve a high-level natural language processing task, such as doing inference. So when does one sentence entail another sentence? So this is a very complex and demanding, challenging task, which deals with, or which assumes that you have some logic understanding. And if you give a model such a task, then it can hopefully induce more intelligent representations of let's say, sentences or texts.